Hey everyone, we got our midterm review here. Hope you take a minute to watch it. I'm going to try to keep it as short as possible. The last one kind of dragged on the last review about 18 minutes. I'm going to try to keep this one relatively short in order to make it as effective as possible. So we're just going to go through some miscellaneous problems here, and you can take notes and you can use these notes on your midterm, of course. So if we have a density problem, my advice to you is going to be to draw the density triangle every single time. You'd have density here, you'd have mass here, and you'd have volume here. We did a practice problem like this today through Socrative, and we plugged in, I think it was for density, we had 19, whoops, sorry about that. We had 19.3 for density, and for mass we had 38.6, and then we didn't know the volume right there. And so we were trying to solve for that. That's a really terrible triangle, but that's okay. We were trying to solve for the volume, so you would do 38.6 over 19.3, and that would give you the volume. You just do 38.6 divided by 19.3. You end up with 2.0 grams per centimeter cubed as your volume. Now, I highly recommend using the triangle. The triangle is going to help. If you plug everything into the right place, then it is going to be effective for you. So that is density. I'm not going to do a lot of practice problems here. I'm just going to kind of go through what's going to be on there and what could be most effective for you. Density of water, important to remember. Density of water is 1.0 grams per milliliter, meaning if something has a density that is lower than 1.0 grams per milliliter, then it will float. So if its density is lower than that, equals it will float, because it has a lower density. If it has a lower density, then it will float. If it has a higher density, higher equals sink. Because if it has a higher density, it will push through that water and sink to the bottom. Whereas if it has a lower density, it won't be able to sink through the water, and it will therefore float on top. So another important note to remember, that one about water and density. Scientific notation. With scientific notation, you want to make sure that you know how to convert from scientific notation to regular notation, and then regular notation to scientific notation. So say you started with a number that was like, I don't know, 826, and then we have 1, 2, 3, 1, 2, 3, 1, 2, 3. 826, a lot, like a billion, a trillion. If we wanted to convert that into scientific notation, we'd have to take this, our decimal would be right here, and we'd move it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 times. You'd move it 11 times. Now the number we started with is greater than 1. Therefore, our exponent needs to be positive. So we'd have 8.26 times 10. We moved it 11 times, so my exponent is going to be 11. You move that 11 times, your exponent is going to be 11. And it's always positive. If the number you start with is greater than 1, then your exponent is going to be positive. If the number you start with is less than 1, then your exponent is going to be negative. So let's do an example with a negative exponent going the other way, going from scientific notation to, from scientific notation to regular notation. So if we had 4.86 times 10 to the negative 6. All you would do for this, and I'm going to try to work through these faster, you would just take this decimal and you would move it. It's negative 6. So that means the number we end up with has to be less than 1. So you would take the decimal and you'd move it 1, 2, 3, 4, 5, 6 times. You'd end up with 5 zeros, so you'd have 0.0000486. Because you're moving the decimal 6 times, you end up with 5 additional zeros. Other practice problems, precision and accuracy. Remember, say I have something and the actual value is 1.5 grams. I have one person weigh it and they get 1.55, let's do that, 1.65, 1.67, and 1.66, and the other person gets 1.47, 1.5, 1.54, and 1.50. If I were to ask you which of these two people, this person or this person, is more precise, what would you say? The correct answer would be this person. This person would be more precise because his values are closer together. If I were to ask you which person would be more accurate, this person would be more accurate because his values are closer to 1.50, which is the actual real value. But this person, if I was asking for precision, all that matters is how close the values are to each other. So this person would be more precise, whereas this person would be more accurate because these are closer to the true value. These are closer to each other. Chemical change. Good example of a chemical change you always want to remember. Baking soda and vinegar. That's an example of a chemical change because it's producing a chemical reaction. Therefore, it's a chemical change. If you just have like boiling water, that's physical. If you're breaking something, that's physical. If you're dissolving something, that's physical. But if you are mixing baking soda and vinegar, that is going to be a chemical change. In terms of diagrams, looking at different types between like element, compound, and mixture. If I have something and they're all the same, like if I have little circles like this, imagine all these circles are the exact same. Then I have something right here where there's this, and then little circles connected to it. Pretend those are connected, little circles with connections. Sorry, these are terrible. They're all connected. They're supposed to look the same. And then down here I have a mix. I have one that's connected right here, and then a few that are like by themselves. These are the type of pictures you'll see on the test. These are bad examples, like they're poorly drawn, but you get the gist. If you have everything that's all the same and it's by itself, it's just like one little circle, just like that, that is an element. Down here, you see how this big circle is connected with these small circles? That makes those compounds. And then down here, if you have all of this mixed together, that is a mixture. So elements, compounds, and mixtures will come in pictures like this. Little circles like this, element. Big circle combined with littler circles, compounds. And then right here, the compound with the elements, that is going to be a mixture. So feel good about that. We're not going to go over atomic models. Make sure you just look in your notebooks for atomic models. That is what will help you the most for atomic models like J.J. Thomson, things like that. Just reference your notebook and you will get those just fine. So we'll skip over anything to do with atomic models. Ions. If you have an ion, like if you have Hg2+, this charge right here, if it is a positive charge, just like that, if it is positive, that means it's losing 2 electrons. So in Hg's situation, Hg will always have 80 protons. Always. That will never change. That's what makes Hg Hg, is because it has 80 protons. That will never ever, for the history of life, change. But because it's an ion, right here, 2+, that means it has lost 2 electrons. It has a positive charge, so it has to have more protons than electrons. Typically, it'll have 80 electrons, right? Because it's the same as protons. But because it is an ion, gonna get rid of that. It's lost 2 electrons, so in this case, it is going to have 78 electrons. 78 electrons. So Hg2+ will always have 80 protons, but because it lost 2 electrons, it will now have 78 electrons. So remember that with ions, when you see that ionic charge, if it's positive, that means it lost a few electrons. So in that case, Hg lost 2 electrons. Okay, another one, neutral. Neutral atoms, if it is neutral, if it's a neutral atom, then that means it has the same number of protons and electrons. The reason it's neutral, if it has the same number of protons and electrons, is because protons are positively charged and electrons are negatively charged. So if you have the exact same number, it's going to be neutral. Whereas like an anion, that's negatively charged, meaning that it has more electrons. and a cation, like the Hg we just looked at, would be positively charged. That means it has more protons. Cation, cats, positive. Cats have pos, they're positive. So cations are positive, anions are negative. Neutral has the same number of protons and electrons. Let's look at our periodic tables. If you look at phosphorus on your periodic table, I'm not going to put a periodic table on here, but if you look at phosphorus, phosphorus is found in group 15. So that means it has 5 valence electrons. If it has five valence electrons and it gains 3 electrons, it wants to gain. It wants to gain 3 electrons. If it's going to gain 3 electrons, what will its charge be? If you're gaining electrons, electrons are negatively charged, so your charge has to be negative. So if phosphorus gained 3 electrons, its charge would be -3. The reason it wants to gain 3 electrons is so it can get a total of 8 and fill out its valence shell. But if it's gaining electrons, it's going to have a negative charge, so its charge will be -3. Okay, still rolling here. Isotopic notation. We've seen that before. Like these would be isotopes of carbon. If you had like C, like that, and then you had like C614. This is how you tell if something's an isotope. You can tell it's an isotope through isotopic notation if it has the same number right here and a different number right here. See how both of these carbon atoms both have a 6 right here, but then they have different numbers right here? That's what makes them isotopes, because what that is saying is that, hey, we have the same number of protons, therefore we are the same element. So they both have 6 protons, therefore they are both carbon. But they're isotopes because they have different mass numbers and therefore different numbers of neutrons. So this carbon has 13, this carbon has 14, therefore those are isotopes, isotopic notation. You can tell they are isotopes if they have the same number down here. So if you see a question and it asks you which ones are isotopes, you choose the ones that have the same atomic number right here, and that will be helpful to you. All right. Isotopic notation again. To get the mass number, remember, so for mass number, you have to do protons plus neutrons. So if you have like 18 protons and 22 neutrons, you identify the element by looking at the number of protons, right? Because protons never ever change. So if we saw 18 protons, I'd look up at my periodic table and I would see 18 is argon. And if I was going to do mass notation, I would do argon dash, and then I do my mass number, remember. So 18 plus 22 would be 40, just like that. Argon 40. You get this mass number, this is mass notation, where you put the element and then the number, or the mass number, and you get that mass number by doing protons plus neutrons. So 18 plus 22, and that equals 40. So that is mass number and mass notation. I know we're going really fast. Okay, another one. Let's see. Sharing is important with covalent bonds. Covalent bonds share. Ionic bonds transfer. So just important key notes to remember. Covalent bonds, they are sharing electrons. Ionic bonds are transferring electrons. So anytime you see share, you know it's going to be covalent. You also know it's covalent if it's 2 nonmetals, whereas ionic is 1 metal, 1 nonmetal. And these do not use prefixes, and these do use prefixes. So there's some differences there between covalent bonds and ionic bonds. Sharing covalent, transferring ionic. Covalent bonds are 2 nonmetals. You use prefixes. Ionic are a metal and a nonmetal, and you do not use prefixes. So like when using prefixes, if you had like N2F5, you have N2F5. Look at N and look at F on your periodic table. They're both nonmetals. They're both on the right side of the periodic table. If they're both on the right side, then they're 2 nonmetals. So that means we have to use prefixes. So in this case, we would have dinitrogen pentafluoride, because we still end in IDE, right? Always end in IDE. We get the di from the 2, the penta from the 5, and we always want to end in ide. So that's an example of naming a covalent compound right there. So that is an important thing to note with covalent compounds. And in terms of covalent bonding, if you saw a picture of covalent bonding, it would probably look something like if you had like CCl4, if you had to draw a picture of that. They're sharing electrons, right? We just talked about that. So you'd have C, and these lines would just represent the sharing of electrons. And then you'd see like Cl, and Cl, just like that. That right there is what covalent bonding looks like, because these lines represent the sharing of electrons. In terms of the shapes of like tetrahedral, things of that nature, tetrahedral, trigonal, pyramidal, and bent, just look in your notebooks for that. We're not going to go through that on here because you have that in your notebooks. To count valence electrons, you count the columns, the group number, like group 1 with like potassium has 1 valence electron. Group 2 with calcium has 2 valence electrons. Then remember, we skip the middle, get over to group 13. They have 3 valence electrons. The group with carbon, group 14, has 4 valence electrons. Nitrogen 5, oxygen 6, fluorine 7, and then you get to the noble gases, which have 8. So remember that for counting valence electrons. If you were given the electron configuration, don't forget about electron configuration. That is another important note to remember, like 1s2, 2s2, 2p6. We're not going to go with that either, just because it's not something that I feel like we need to review. Everybody did relatively well on that. Remember, you can tell like what element it is. If you had like 1s2, 2s1, you can tell which element it is by just adding these small numbers together, and that's the atomic number of whatever element it is. So if it's 1s2, 2s1, you go 2 plus 1 equals 3. Which element has the atomic number 3? And that is lithium. So if you just add these small numbers together, you can tell what element it is. So that's a good thing right there. For electronic configuration, we're not going to go through that too much. I can do examples for you later if you would like. Lewis dot diagrams. Remember Lewis dot diagrams. If you're doing a Lewis dot diagram, you want to fill up all the sides first. So you wouldn't want one that had 3. If it was like BR and it was supposed to have 3, it should be like 1, 2, 3. Shouldn't be, if you had like BR, you wouldn't want like 1, 2, 3. You know what I mean? You want to separate them so they're each on separate sides. If it looks like this, if there's 2 on one side and 1 down here and 2 empty sides, then it's wrong. That would be incorrect. You don't want 2 on one side. You want 1 on each side. Crisscrossing is another important aspect. We want to crisscross our elements, like if you have like lithium, which is its charge is 1+, and sulfur, whose charge is 2-. You would crisscross these. Remember that. You always want to crisscross. So you'd end up with LiS2. I'm sorry, this is really bad handwriting. LiS2. And that's just an example of an ionic compound. So in the end, LiS2, the name for that, because it's ionic, we don't use prefixes, so it would just be lithium sulfide. Just lithium sulfide. Another side note, just to remember, crisscross everything. Always crisscross. Anytime you see a chemical reaction, it's not really going to involve very many covalent compounds, so always remember to crisscross. Also remember that anytime you write oxygen or any of the other diatomic elements and it's by itself, you have to add a 2. You absolutely have to add a 2. So if oxygen is by itself in a reaction, you need to add a 2. It can't just be O. It's got to have a 2 right there. The other elements that need that are, we have hydrogen, oxygen, chlorine, fluorine, bromine, iodine, 1, 2, 3, 4, 5, 6, and nitrogen. Each of those elements, when alone, add a 2 subscript. Every time you have to add a 2 subscript when those are alones. Alones, plural, that doesn't make sense. Other thing to remember, whenever we balance equations, we do so that we obey the law of conservation of mass. Law of conservation of mass. That's just what we do when we're balancing equations. That states that matter is neither created nor destroyed. So we follow the law of conservation of mass. Matter is neither created nor destroyed. That is why our elements or our equations have to be balanced. When you're balancing an equation, you can only change the coefficients. Those are the numbers, remember, that come in front of each compound or each element. You can only change the coefficients. Like the numbers, like if you had 202 right here, this number is the only number you can ever change. This number right here has to stay the same. So you can only change the coefficients. And in every balanced equation, in all balanced equations must have the same number of atoms. That will be beneficial for you. All balanced equations must have the same number of atoms. So that'll be good. Balancing equations, I'm not going to do examples up here. We've done so many balancing of equations that you should be masters of the balancing of equations. And then different type of reactions. Remember that like synthesis, like double replacement is when two things are switching spots. So it's just flip-flopped two things. Like if two elements switch spots on each side of a reaction, that's double replacement. Synthesis is two becoming one. Decomposition is one becoming two. And then, so like if you had three things in like a picture, and you had like 1, 2, and 3 all separated right here, and then you had the production sign, producing, and then on this side, all of the circles were combined, that would be synthesis, because they're all combining, right? If it was the opposite, if it was going from all combined to all separated, that would be decomposition. So just remember that as you go. But my biggest thing is make sure you crisscross when you do ionic compounds. Make sure you look through your notes at all times. Don't try to answer a question without looking through your notes. We have to balance several equations on here. Other thing, just try to keep your, would be, sorry I froze there for a minute, a polyatomic ion would be like PO4. So when you're balancing an equation, always keep that together. I think we're going to do well on this test. If you watch this video, I think it'll help. I know I seemed rushed, but it's because I was trying to get through a little bit of everything just to give you an idea of exactly what's going to be covered on the midterm. So best of luck on the midterm. Hopefully you watched this, took some notes, and are getting something out of it. And I will see you all for the midterm. Farewell.